Before we get started with today's video, I would like to point out that this video will be published on BitChute about a day or more before it premieres on YouTube. Hello, this is tchapman500, and today I will be showing you some changes I've made to my demo CPU. Now, the GitHub repository, link in the description, has three branches. The preserved branch, which is for the original Logisim, the restored branch, which is the branch where I brought the CPU to a working state so that all of the instructions would function properly. And then we have the enhanced branch, which is what I'm working on now. So first, from right to left, if we scroll down here, we can see that we are using some special circuitry attached to register 7. Register 7 is now the lower half of the stack pointer. The upper half is right here, 08 hexadecimal. So you have 2 kilobytes for your program, followed by 256 bytes for the stack. And we also have a new signal to put the stack pointer onto the address bus. I've also moved the clock to outside the control unit. It now goes to every single register. Now you might have also noticed these things. So we can put the program counter onto the data bus. Now the only instruction that can put the program counter onto the data bus is a call instruction. And the call instruction will push the 2 bytes that are in the program counter onto the stack. I'm going to show you the flags register, which is now a 2-bit register. The first bit holds the 0 flag. The second bit holds the carry flag. So we do all of the equality tests with just 2 flags instead of 4. By the way, this does mean that the jump condition was changed, so the conditional jump is now incompatible with the restored version of this CPU. So the arithmetic logic unit has been modified. I've modified the AND gate so that it is both a test operation and an AND operation. When it's a test operation, that's this line here, it'll set the 0 flag, and when it's the AND operation, it will output to the output register. So the flag generation circuitry is now much simpler, and the way that we put the data and flags onto the bus are also much simpler. And now for the control unit, I basically replaced all of the combinational logic with ROMs. Now, had I done nothing to optimize things, we would end up with 8,192 control words to control this processor. I optimized it and ended up with, I think, 640 control words. So the control logic checks to make sure if each of these ROMs are active, and if none of the ROMs are active, then this ROM is active. And this part of the circuit right here is essentially a multiplexer, which just makes sure that only one ROM is writing to these signals at a time. Now to load the instruction register, I do not use any ROMs. Instead, I hardwire that logic into the first step of the clock. Now for this processor, we have to reset the CPU and then run up the clock. Right now there are just no op instructions, but as you can see, we have signals going to the instruction register, the program counter, and the RAM. Now here is the entire program so far for generating the ROM files. So what I've done is I've made a set of constants which represent control signals. I even made some that are a set of OR operations between 2 or more constants. Here's the entire data set for the first ROM. This one is complete, and you can kind of see what all I did. Now the call instruction was quite interesting because I just about ran out of steps to execute this instruction, and as it turns out, the step clear signal, which is right here, I don't need that for the call instruction, because once the call instruction finishes executing, the stepper overflows, essentially resetting itself. Now the conditional jump, this is the second ROM, which I have not been able to test yet. Yet these are basically all the same, except whenever the jump condition is met, we take whatever's in the address register and put it in the program counter. Now the third ROM I haven't programmed in yet. I'll get to that later. The fourth ROM I've partially programmed, so this is what it looks like so far. And these are all of the arithmetic logic unit instructions. Now the main function just writes whatever is in these arrays to binary files, and I can load these files into Logisim. Now there's one thing I would like to point out. You may have noticed in a previous video that I tried to make a 16-bit processor. Well, I had to kind of put that aside for now because it turns out that the 16-bit processor was a little bit too ambitious. So it wasn't the 16-bit part that was ambitious, it was what I wanted to do with it. So stuff like interrupt handling, function calls, stack management, floating point operations, stuff like that, instruction pipeline, stuff like that I wanted to have in the 16-bit CPU. But that was quite a bit beyond my skill level, so what I did, because I had no choice, is I set it aside and decided to enhance the demo CPU to get a bit more experience with the basics before going into more advanced stuff like instruction pipelining. So there are a few instructions left that I need to implement. By the way, I cut out the part of me implementing the rest of the microcode. The processor does not yet have the hardware to process some instructions, so I just left out the microcode for those instructions altogether. Anyways, now it's time to load the microcode into the ROMs. This is the first ROM we're going to load, so we go to Load Memory Image. We're going to load the Conditional Jump, Little Indian, OK, and that is that ROM loaded. Now there are some extra instructions that also do not have an embedded operand. So we're going to go Load Memory Image, Extra Operations, Little Indian, and there we go. Might not look like it did anything, but it did. Next we're going to load everything else. So that is all 4 ROMs loaded. Now, to test this, we need to write a program. So this is the CPU definition for this processor, and whatever program we write, we need to make sure that it fits within whatever's defined here. And we will write a program. Now to compile the program, I'm not going to be manually creating a binary or hexadecimal file based on those instructions that you saw me write. Instead, I've used a tool called Custom ASM, which is a custom assembler that allows you to define the instruction set for the processor and then assemble a binary from an assembly code. Well, this is an inconvenient delay. I forgot to switch outputs on OBS, so we basically get stuck on the GitHub page of Custom ASM rather than on Logisim. So now I have to re-record a good portion of this video. One moment, please. Okay, so now that I'm recording Logisim instead of the web browser, let me load up the program that I ran while unknowingly recording the web browser, and I'm gonna run it. But before I do, this is just a test program to make sure the push and pop instructions as well as the ALU and other things work properly. Something basic, what I haven't tested before doing this thing. So we need to reset the CPU before we run the program, and then I'm going to have auto ticks enabled, and register 1 now has the output of the program. Typically, it would be in register 0. So yeah, this is a program just to make sure that the stack management operations work. In a future video, I intend to implement stuff like interrupt handling. So we will be able to set an address for the interrupt service routine, enable, disable interrupts, clear the interrupt flag, etc. This will require an extra ROM for the instruction decoder and a few other things that I'm not quite sure how to do, but this is a good start, and I would like to leave the CPU in a state that can be run without error at the end of each video. Now I will make a few modifications before we end off the video. First off, I want to move this clock signal over to here, so it's on the same line, but I just want to make room for the interrupt handling circuitry, which I'm hoping will be up here somewhere. Next, I'm going to move this over so that I can move this over. Perhaps I should make the clock be over here. I'm going to put an SR latch on this reset signal. Now the reason for this is because the reset should only go low when the clock is low. So I am going to negate the bottom input of the AND gate, wire the AND gate to here, and then bring the clock signal down so that if the clock is high and we hit the reset button, let's try a NOR gate instead. So if the clock is high and a reset is triggered, then the reset line remains high until the clock goes low. Then the reset line is cleared. So let's bring this back up to here, and we can make this a little bit more compact. There we go. Also drag this down a little bit. So I'm going to save that. Going to commit it to the GitHub repository. I'm going to run the program again. Actually, I'm going to explain what it does, manually ticking through the clock. So the first instruction loads 18 into register 0, and since all the displays here are in hexadecimal, it looks like it's 12. The next instruction pushes that 12 onto the top of the stack. So now the stack pointer has been reduced. It basically just wrapped around. There's no overflow protection on this stack, so if it overflows, it's just going to continue operating, but it might malfunction eventually, and you'll have an interesting time trying to debug it. So it's now going to write 18 at this location and immediately go to the next instruction when the clock goes low. So if we take a look at what's in the RAM, scroll down to where the stack is, we see the 18 in its proper location. So now it's going to load 2 into the accumulator. So let's check out the state, and the accumulator is right here. Oh wait, I forgot that there's a pop instruction to take whatever's on the top of the stack and put it into register 1. Now it's going to load a 2 into the accumulator. And just like that, the accumulator has a value of 2. Now it's going to shift whatever's in register 1 over 2 bits to the right. So now the output register, which is here, has basically 18 divided by 4. So that's 18 shifted to the right 2 places. And it looks like it's going to be set back into the accumulator. Yep. And the next instruction will be an add instruction. So 18 plus 4. The output now has 16 hexadecimal, which is 22 in decimal, which is the correct answer. And it looks like the next instruction is going to store that into register 1. Yep. The next instruction is a jump if carry, which there's no carry flag. So as you can see, for the flags register, there's no carry flag. Here, let me move that closer. So this jump instruction is just going to be ignored. Next, it's going to do an unconditional jump back to this instruction. So that's basically a halt instruction. Let's reset that. And I'm going to modify this program. Let's put A4 into register 0. And now it should jump back to the beginning. I don't think it's going to jump back to the beginning. The flag's register is 0. Oh dear. Let's try shifting it over just 1 byte. And actually, that should guarantee that it overflows. Yep, it overflowed. We are back to the beginning of the program. And we can see here that the carry flag is set, which means that it overflowed. By the way, this program basically uses a push instruction followed by a pop instruction to move data from one register to the other. Now, of course, there is a way to do that without using the stack, but I'll leave that for you to implement yourself. I hope you enjoyed the video. Don't forget to rate, comment, subscribe, and share, and I will see you in the next video. And by the way, if you want to support my work, you can do so via Patreon or Subscribestar. Links are in the description. This is T. Chapman 500 signing off.